Okay, we will now start the session. So before I start the session, there is a little talk I just want to discuss. So, in that equivalent conditions, correct? This theorem. In 1 implies 2, this proof is incorrect because when I was thinking about the proof, I was thinking about that every no vacancy type of thing. So the proof is not this. So we just change the proof little bit. The thing is that what we have to prove? We have to prove that every omega set is dense in X. On the assumption that every open set is non-mega in X. Okay. So let's say A, B are omega set in X. Suppose on contrary that A is not dense. Suppose on contrary that A is not dense. Then what will happen? There exists an open set, I mean non-empty open set obviously, such that, okay, let's say open set U. Open set U not equals to 5 such that U intersection A will be empty. So then hence what will happen? A will be inside of, sorry, not A, U will be inside of X minus U. U will be inside of X minus A. Now, because A is omega, X minus A is mega, and therefore U is a subset of a mega set, so U is mega, but U is an open set, it should be non-mega, so which is a contradiction. Since X minus A is mega, A is mega. Okay, sorry, U is mega, which is a contradiction. U is mega, which is a contradiction. Hence, A is dense. So this is the proof that form 1 implies 2, not the previous one. Okay, another thing is that in this proof, one of our participants, I think it was Pallavi, pointed out the fact. So you cannot have S intersection U equals to 5. Okay. So because suppose X intersection U is 5, or other way to say that whatever open set you have, at the same time S intersection U is 5 and S intersection U is 5 is not possible. Okay. So try, you will also get the solution. Like take an element that which is not in there, I mean, X intersection A, there is an element, let's say, and from there you will get a contradiction. Okay. That means that is also true. Now we will just introduce basic idea of topological game. So the thing, let me tell you what is the background of this. It's like the first half of 20th century, like around 1935. So a group of mathematicians, including Stephen Banach, used to sit in a coffee shop. Okay. So there they discuss mathematical problems, and later, around 1935, Stephen Banach started recording all their discussion in form of problems and solutions. Okay. So there, one day, problem number 43, Mazur. Okay, so Mazur was another mathematician that time, Poland. What I'm discussing is Poland. So he observed that the pair property, it's related to, we can represent their property in a different manner. That later came as a game. So he posed a problem, and later Banach solved that problem. So that's why first topological game problem is called Banach-Mazur game. Okay. So it's like they have somehow introduced that idea. Okay, that book where Banach used to write down all this stuff. It's called now. It's called very popular and it's known as Scottish book because the name of the coffee shop was Scottish Cafe. So it's called Scottish book. So this is Banach-Mazur problem. Game problem is actually 43. Problem number 43. But the term, the topological game was not. They did not coin that term. Later, in I think 1975. Another mathematician, Talversky. So he introduced this term, topological game. But before that, initially, like 1957, there were many mathematicians started working on this problem of infinite positional game. Okay. So where you have, but there are two players plays against each other, and they have this playing is like. You can play it for infinitely many times theoretically, and all of them has perfect information. So there is no hidden, nothing is hidden. So both of them have same information, and depends on their information, they are playing. Okay, so what's going on in a topological game? A topological game is a game played by two players. So here we have two players. We in general say player 1 or player 2 or alpha beta. Okay, so here two players will play games. So in a topological space. So instead of card and something like that, what they will going to use? They will use the points of the space, or sometimes, most cases, open set of the space, or some other closed set, open set, compact set. They will use as their bait. Okay. So not as a card, but as an open set as a bait. And obviously there will be a criteria for winning the game. Okay. For each player, obviously each player wants to win their own game. So that means what? The idea is that you can generate a property, or you can we have a separation property. We know that a space when we call it a first countable space, second countable space. These are the properties of a topological space. So using game, so you can introduce a game, and you say that if a topological space satisfies, and if a topological space has a solution in the sense that if there is some strategy for one player that I will define all the term strategies and all sort of thing. If use this strategy, he will win the game. So that means there is some type of determinacy. Like you can determine that one player will win, should win in that game. So depends on that, you can define different type of topological space. Okay. Like topological, so here actually you are corresponding topological property of a space to a game. Okay, topological game. So that's the idea. So we'll see that there's space, that property corresponding to some game. So if you have some game, you can always going to have a topological property. So there is a one-to-one correspondence between the game and topological properties. Okay, second countable can be posed under this one game. So, like if a space is second countable, this game can be solved. Solved in the sense that there will be a strategy for one player, at least this one player, something like that. Okay, so this is the idea. Like you want to now study topological spaces using games, in games of between two players. So obviously that was the initial, but recent work is like instead of just studying topological property, what do we have to? So like most cases, if you look at the recent papers, the idea is that you have a function from one space to another space. Okay, and we want to know what will be the set of discontinuities of this function. So now we want to know, suppose let's say this topological space has a property which is determined by a game, which was generated by a game. Then can we say that this set of discontinuity point will be small set, a big set in the sense that what I discussed today morning. Okay, like ratio dual or it's a maker, non-maker. What type of set it will be? The set of discontinuity of a space. If the space is generated by a game, like satisfy some property. So that's the basic idea overall. The working community in this area, like they want to study the set of discontinuity or many other things using the game properties. So from game we have a topological properties, and now we have a topological space with that specific property. Like second countable topological space is a second countability is a property. Now we have another property which is not second countability but a property which is generated by a game. And now under that property you have a topological space, and you want to study whether that function defined on that space has, if you want some property, whether it satisfies that property or not. Okay, that is the idea. Okay, so now I think I should start discussing. So first we will discuss Shoke game. Okay. I think it was introduced around 1967, okay, or maybe 19. Yeah, it's around 1967. So the mathematician Shoke introduced this. Ghost of Shoke introduced this game. Okay. So what is this game? So game obviously played by two players. So we have now two players. Okay. So two players. Let's say alpha and beta. So in this game, beta, the player beta always start the game. Okay. So the condition is that beta starts the game always. How beta will start the game? Beta will choose a non-empty open subset of X. Okay, we are playing the game in a non-empty open. Let X tau be a topological space. Okay. So first, beta will always go first. Beta will choose a non-empty open set. Okay. So let me put this way: beta and alpha. So beta choose a non-empty open set. So B1 is a non-empty open set. Now, what in response to beta's bet, what alpha will do? Alpha will choose another non-empty. Alpha has to choose. That's the condition. Okay, condition of the game. Alpha has to choose another non-empty open set. Non-empty is important. Another non-empty open set, which is a subset of B1. So alpha has to choose A1, and A1 should be a subset of B1. Clear? Okay. Now next move will be a move for beta. What beta will do? Beta will choose again another non-empty open set. So whatever A and B1 were discussing, all non-empty open sets. So he will choose another non-empty open set. Let's say beta 2, which will be subset of A1. So he will choose beta 2 and beta 2. Sorry, B2, which will be subset of A1. Again, this next move will be one move for alpha. What alpha will do? Alpha will choose a non-empty open set as subset of B1. A2. So in this way, they will continue this procedure. Okay. So first you have beta n. Let's say it's in some nth move. So then alpha will choose an such that an is a subset of Bn, non-empty open. It will continue. When will stop? If so, they will generate. So if they go this way, it will generate a sequence of open sets, non-empty open sets. So it will generate a sequence of like B1, then you have a subset of A1, then you have subset of A2, B2, then subset A2, and so on. So this play, this whole procedure will generate a sequence of non-empty open subsets of X. We will denote this sequence by, so we will write, denote this by, okay, so we write P n comma a n or whatever we want to write, that doesn't matter. So let me write P n comma a. And this will be called a play. Okay. This sequence of open set will be called a play. So this is called a play. And any first n move like B1A1 or B1A1, B2A2 will be called. So any finite sequence of this play, okay, will be called a partial play. So any finite sequence, or better to it's not actually subsequence, sequence of the play will be called a partial play. Okay, what do you mean by partial play? Like consists of first n moves. Okay, so you cannot have like A1, B1, A1 and B2. This is not a play. What we are saying that it should be first n moves of both players. Okay. So play is a partial play is like dk ak k equals to 1 to n. That is the first n moves. The first n moves of the both players. Now, in choke game, we have the condition for winning of both player alpha and beta. So we'll say that alpha will own the game. Okay. If you move this way, intersection of AN will also be equals to intersection of BN if it is non-empty. If you play a game in such a way that intersection of AN is intersection of BN, so obviously practical is not possible, but theoretical is possible. If this is non-empty, then we'll say that alpha will own the game. then alpha will win the game. So this is a rule of the game. It's saying that if we have generate a play in such a way that if intersection of A and not equals to 5, we'll say that player alpha win the game. Otherwise, we'll say that player beta won the game. Okay. So otherwise, beta won the game. Okay. That means if it is empty, then beta will say that beta won the game. That's the condition. So this game is known as Soke game. Okay. So this game is known as Soke game and denoted by So this is the notation we use in general. Soke game. CH of X. So is it clear what is the play and what is the winning criteria for both players?
For beta to play, we should choose a subset such that there is
no. It's like it will become empty. Like they are both choosing non-empty open set.
Yes.
So obviously they are playing against each other. So whatever B1 choose, then A1 will choose, then again B2. So in such a way, the strategy for A1 should be to make that intersection non-empty. Suppose its and strategy for the beta will be to make that intersection empty. That's the idea.
again at the same time the intersection of A and B will be the last term.
No, it's a last return because it's a countable. It's running. Okay, it might cause some step it's become empty. It's not going to happen in general. They both will work so hard that it will not going to end at any step. At least A alpha will work so hard that it will be non-empty. Okay. You have open set. Yeah, it's a topological space, finite topological space, it might possible. But if we have only finitely many open sets. But in other cases, it's like, okay, let's say an example of finite topological space. Let's say X is A, B, C, D. Tau is X. Then A, B, Next. Is it an topology? Union is there, intersection is there. It's a topology, correct? Now let's say you are player beta and I'm player alpha. So what shall I do? So let's say you are beta, so choose your weight. So let's say B1. Your B1 is single turning. I will choose A1 as single turning. You have to choose single turning and it will be non-empty and I will win the game. So whatever, choose anything. Any other thing, AB. I will always going to win the game. In this game, in this space, player alpha always has to win strategy. Actually, in a compact space, the player alpha always will have the winning strategy. Okay. Beta ones, so even let's say you are beta one. That will be your first move. So whatever move you will do, what I will do, I will just continue in this case. So let's say you choose A. I will choose A. Then you have to choose A because you cannot choose an empty set. You have to choose a non-empty set. So it will continue in a secure.
Otherwise, always one will choose the same.
Yeah, alternate is there. Alternate is important. Because if you have an infinite set, you can always choose alternate.
One player gives up only this
No, both player will choose. But in this case, because it's a finite, it's not possible. But let's say you choose in a R. So let's say real line, you are a player alpha, right? Beta. Your choose will be B1 will be the first. So what will you choose? Choose an interval. That will be easy to handle. Okay, open interval B1 is open interval 0, 1. Now I am alpha. My task is to not to make it is empty. So I will choose A1, let's say 0, half. So what we will do? We have to choose a open subset of that. So you will have it will be 1 by 4. Okay, you want to choose 1 by 4, 1 by 4. Actually, your motivation should be 0, 1 by 4 because you are trying to make it in such a way that it will move towards 0. So that 0 is not over there and it will not go into contact. Right? Anyway, so one by 2. This way.
1 by 4, 1 by 2.
Oh yeah, sorry. Okay, make other way. 0 is will be greater, I guess. Make 1.6, otherwise you will not going to write any type of things. It's difficult to write. Okay, anyway, you can write 2 square 1 by 2. Yeah, 1 by 4, 1 by 2. So then again, A2 has to choose in such a way. So let's say, suppose that A2 choose what? 1 by 3, 1 by 2. Then again, you have to choose. So, like, you have A3, you will choose them. Okay. So, what you will choose? You have to choose in such a way that your task should be to make it empty, and the player alpha's task is not to make it empty. That's why they are actually tag over. Both are playing in their best. Okay. That's the idea. So we prove that in a bare space, like it's include that real line, the player alpha always has a winning strategy. So, or other way to say, we'll see it, okay, what it is coming in this case. So this will go on in this case. Okay, I have said many times the strategy. What do you mean by a strategy? Okay, let me define it once. You got the point. What is going on? So we have each player is trying to mold the play in such a way that they will win the game. Yes, it's possible. Yeah, that's the possibility is there. So let's say we have to define strategy or a winning strategy, but let's say here is a no strategy for the one player. Does it mean that other player will have the strategy? No. There will be no strategy for the other player. It's no guarantee that other player will have a strategy. It might possible in a game, both player has no strategy. Okay. But if one player has a strategy, obviously other player cannot have a strategy to win the game. Because otherwise, it's not possible, it will contradict each other. Both will play in such a way that it will contradict each other. So then you can say that this is winning strategy. I mean, strategy, both players can do with strategy, optimal strategy, but you can say that both players has a winning strategy at the same time in a space. Otherwise, it will contradict. Who will win? So it will contradict. It cannot be, it can be draw, but it cannot be a winning strategy. In this case, you have to choose in what sense it will not implement. So let's say it will be like in this form 0, 1, 0, half. Suppose both are playing this way. If we continue this way, what will be the intersection of all this? It will be empty set. So in this case, player beta will win the game. Obviously, alpha will not going to do it in this way, but no, it's like you know that this sequence. If we have this sequence, it's moving this way, and you know that what will be the intersection. This is let's say beta is playing. P1, A1, P2, and it's a perfect game. Both have a perfect information. But let's say that the player alpha is an idiot, and he whatever doing beta is like 0 half is doing it like that. So in this case, obviously the intersection will be empty, and beta will win the game. You cannot say that okay, but obviously the problem with that physicality and theoretical. Physically, obviously, you can only have the n number of moves, but mathematically, you can take the limit. Limit n tends to infinity. What will happen if they follow a path? Okay. Now, what do you mean by strategy? So, strategy means obviously you understood properly that it's a rule of playing a game. Correct. In whatever context you have, whatever context you have some rule to play the game. That okay, I will play this game in this following pattern. It's okay. We can say formally, informally. But what's this mathematically? So mathematically speaking, a strategy for the player alpha is a sequence of tau value mapping EN. So it's a sequence of tau value mapping. So that's a strategy. We are defining a strategy in this following way. So what is tau value mapping? That means whatever domain of the function, you will get a open set. Tau value mapping means the value will be an open set. Okay. Okay. Domain such that okay, the domain of TA or ECN defined recursively as follows. So what will be the domain of the function? We are defining the domain in the following way. Okay, what is the domain of? So we are saying domain of T1 consists of all this sequence of one element where B1 is an open set. So you can see that. So this is the strategy for the player alpha. So whatever B1 will choose, the player X. So B1 is a non-empty. The non-empty. In X. So whatever player beta will choose B1 depends on that A1 will be chosen for the player alpha. So that means T1 is a mapping for all this T1. That means in this case all the non-empty open subset of X, and for this you have a value. Okay. So T1 is like that. Whatever it's a domain, and you have a value for T1. That can be different value. But for different choice of beta, for one beta one, it can have several many A1. That's also possibility. But the thing is that T1 should be a subset of B1. Whatever value we will choose, it should be a subset of B1. Is it clear? T1 of B1 should be a subset of T1 of B1 should be subset of B1. Because that will be A1. T1 B1 is nothing but your A1, which should be a non-empty. Is it clear? Okay, tell me what will be the domain of TT. It will be, so for alpha, they are not considering its own move. he is making his strategy depends on the previous moves of the player alpha. Sorry, player beta. Alpha is making strategy. I mean, alpha is playing based on the choice or the moves that beta has already made. So this domain of T2 is a sequence, finite sequence, or let's say pair of elements B1 and B2, such that what is such that B1, yeah, B2 should be subset of T1 of B1, and B1 is belongs to domain of T1. Correct. And obviously beta 2 is non-empty open set. That's understand. Yes. Now we have depends on these B1, B2, he will make a choice. Okay, you see that B1 it obviously belongs to T1, the domain of T1. Here from here you are taking B1, and beta 2 should be subset of T1 P1 because beta 2 should be subset of A1. Okay, so that's why this is your here. Okay. So we have a sequence now B1, B2, and such a way that this is like. Okay, obviously your A2, which is nothing but T2 of B1, B2, whatever you will choose, it should be subset of B2. Okay. Whatever you will make A2, that choice that alpha will going to make, it is a non-empty open set. Okay. And this should be beta. And you have it has different choices because choice of B1 you have so many choices. You have many other possibilities. It's not just a fixed number. Okay, so if you go in this way, recursively, what we are defining domain of Tn plus 1 will consist of a finite sequence B1, B2, Tn plus 1 such that okay, we think we have to continue this after. Okay, we have 20 minutes. Okay, B1, B2, Bn plus 1 such that what will happen, tell me, if you move that over here, beta 2 should be subset of T1 of T1. So then in this case what it will happen? Beta 1 to Bn should be subset of, sorry, Bn plus 1 should be subset of, yeah, Bn plus 1 should be subset of Tn of B1, B2, Bn. And what will happen? B1 belongs to domain of T1. So that means actually we should write this condition first, then it is this one. Because this B1, B2, Bn, all of this should be should come from the domain of Tn. That's how we are getting the domain. So now we have a function. Sequence of function, which is actually a strategy. So like define choice of B1, you are making a rule. So to know that function is nothing but a rule. So for each choice of B1, you are now making a choice. That's your strategy. You have a function which will tell you if he chooses this B1. So now initially, let's think about that. He made us a strategy. Okay, if he move this way, so think about that you are playing a chess. You have a function. So suppose he moved a particular B1. Depends on that, he has a function, this will produce some A1. Okay, he choose another B1, will get another sequence, another subset. So that's already determined. Its function is already from the very beginning you made a function or a sequence. Better to say you made a. See, you already have a tools which is a sequence of functions, and depends on the choice of each move of the other player is making his bet. Okay. So that's the idea. That's why it's called a strategy. Clear? What we mean by strategy? Okay. Good. So any element, now if you take the union of all these domains, so each element of union n equals to 1 to infinity, domain of Tn is called a T-plane. Sorry, a partial T-plane. It's called a partial T-plane. That's the definition of a partial T-plane. So whatever element you will have over here, like B1, we just have one B1. That's a partial T-plane. Or any element of the domain is called a partial T-plane. That's how we have defined partial T-plane. Okay. So a sequence. So now we are defining a sequence Dn. N belongs to N, such that okay, I think I should put different notation over here. Sequence Bk, A belongs to N, such that B1, B2, Bn belongs to
minutes is there. You stop at the join.
Just 1 more.
2 more minutes time.
Okay.
3 more minutes time.
So such that this N it belongs to where it belongs domain of Tn for each N. So if we have a sequence of Tn such that any N terms belongs to the domain of Tn is called a T-plane. Is called a T-plane. You can see that you have a many T-planes. You have actually, if you have an infinite collection of open set, you will have the infinitely many number of T-planes. Okay, for a given strategy. Okay, so we'll say that alpha win the as a okay. First, let me. So the strategy will be called a winning strategy for the player alpha if alpha wins each T-plane. Okay. So the strategy. Let's say T is our strategy. T is the sequence. Okay. T means here that sequence. Then the strategy T is called a winning strategy for the player alpha if alpha wins each T-plane. That's how we are defining winning strategy. So whatever we have, whatever T-plane they play, or he will alpha will win the game, then the strategy will be called the winning strategy for us. Okay. So and then we will continue from here. Is it clear what we mean by winning strategy? You can have different T-plays, but if each T-play won by the alpha, then we call it's a winning strategy for alpha. Similarly, you can define winning strategy for the beta. So we are not defining it, but it's just a similar way. So we will continue from here. Can you inform online participant? Online participant, please note that we'll continue the session maybe after 3:30 because in our department there is one professor is retiring today, so he has farewell. Shall we start? So till now we have defined what is a choke game, and then we define the strategy. You know, what we mean by strategy for a player alpha, and then what we mean by a winning strategy for the player. Okay. So now suppose in a space you have a winning strategy for alpha. We'll name that space. Okay, so we'll differentiate the space which where we have a winning strategy for the player alpha and a space where we don't have the winning strategy. Okay, so we'll say that a space is called quickly alpha favorable topological space. Is called quickly alpha favorable if there exists, this is the definition, if there exists a winning strategy for the player alpha.
Missing that.
Can you see this discussing? So we'll call a weekly alpha. Similarly, you can define other like weekly alpha, not alpha unfavorable. Okay. So it's this type of thing. Now you see that I use the word weekly alpha favorable because there is a notion of alpha favorable. So like what happens in this winning strategy, in the strategy, the way we define the strategy. So we always consider, so whenever we are considering the innate move for the player alpha, so he's considering the first innate move of the player beta. Okay. So all the previous moves of the player beta is considered, alpha is considering and then making his bet. Okay. Now let's say instead of looking at all the previous moves, all n moves, he's just looking at the last n moves. Okay, so we are defining, let's say, let definition is there. So a stationary winning strategy for the player alpha is a sequence, let's say T of tau values mapping such that, so what is the domain in this case? Domain is just such that this T of beta n is only subset of Bn. So like works for each n. So what's going on? So beta makes his move B1, and in response to that, alpha makes his move A1. So which is our T of beta 1. Now whenever he was making it, now beta to another move, so beta 2 is move is there. So now till now when you are discussing winning strategy, so A2. So if you look at the winning strategy and difference between stationary strategy, so A2 is now functions of T1 is 1 and T2 is only of B2. This is subset of B1 and this is subset of B2. Tn is subset of Bn. So Tn is not now a function of B1, B2, Bn, it's just a function of Bn. The last move he is considering. Last move of alpha is only in this case. So what is the domain in this case? The domain of T1 is obviously B1. B1 is a non-empty open subset of X. Okay. And we have T1 of B1 obviously going to be subset of B1. And what is the domain of T2? It's just B2. Such that B2 is a subset of T1, B1. And B2 is a non-empty open subset of X. This will be the domain of T2. Okay. Just one single open set. So this does not depend on the sequence, that finite sequence is missing in this. Okay, so in general, our domain of Tn plus 1 is a Tn plus 1 such that Tn plus 1 is non-empty and open, comma, and Bn plus 1 subset of Bn. Bn is from the domain of this is the way recursively we can define the domain of Tn plus 1. Okay. And obviously, similarly, you can define a partial T-play and a T-play. Like if we have a sequence of Bn's, which where Bn belongs to the domain of Tn, you have a T-play. Now, if there is a T-play, which is, now similarly you can define, in this case, we can define T-play then that if a strategy T will be called stationary winning strategy, then stationary strategy is called stationary winning strategy. Winning strategy. If each T-play is owned by alpha. If alpha wins each T-play in this case, where stationary T-play you can say also define T-play or whatever. So in that case we'll say that the paper space has, so a space will be called alpha favorable if there exists a stationary winning strategy. So a space is called alpha favorable if there exists a stationary winning strategy for the player. So you can see that if a player has a stationary winning strategy, then it's also going to have, it's also a winning strategy in that sense. So what you will do, just define a function, the same value you will define, and that will give you the same function. Okay. What I'm saying is, let's say a space has a space is alpha favorable, then it should be quickly alpha favorable. Alpha favorable means there will be winning strategy. So only depends on the last move he is making. Okay, so define the same function. So suppose, so every alpha favorable space is weakly alpha favorable. Every alpha favorable space will be weakly alpha favorable. Because he is considering the last move and fix whatever T and B1, B2 will end. So we will say yes, T and B1, B2, Bn as okay, we are using same notation. Let's say it's a weak list, so I put weak list strategy alpha, and then you have Tn and Bn. You put the same value. This will give you the same detail. Because in this case you have this n inside. Because of that you can consider. But there are some cases where we have weakly alpha strategy. That means the space is weakly alpha favorable, but it is not the alpha favorable. Anyway, so that's how we define space is either alpha favorable or weakly alpha favorable. Let me discuss a little bit. So suppose we have two strategies for a given period. So let's say let sigma and T be two strategies for the player alpha. Then we call sigma defines T. Then we say sigma defines T and write sigma if each T play, each sigma play is our key play. What do you mean by that? That is domain of sigma n is a subset of domain of Tn. So whatever elements you have in the sigma n, they are also elements of Tn, and sigma n of B1, B2, Bn, because B1, B2, Bn is in sigma n, which also will be in Tn. So this will be subset of Tn of B1, B2, Bn. So this is what we mean by another strategy defines one strategy defines another strategy. So it's a refinement of another strategy. Okay. Why we need that? We'll see that. Why we need? Because let's say we have a basis for a space. Suppose you know the basis for a space. So then, in general, we will let's say consider pi base for a space. Then whatever open set you will have, you can always consider a subset over there, and that's how instead of looking at the open sets that plane, you can always consider a basis elements instead of that. Okay. So here you will need the notion of sigma refinement. So this little exercise, do it. I will do it later. If P is a pi base for the topology tau on X, pi base for the topology tau on X, then for any strategy T for the player alpha, there exists a refined strategy sigma, where domain of sigma n consists of basic open, obviously non-empty subsets of X. I mean, not basic one, pi basic, I can say. So that means you have a domain B1, B2, Bn. Now instead of that, you have a new strategy. You have a refinement where that you are, instead of B1, B2, now you have C1, C2, Cn, where C1, C2, Cn are from the pi base. Okay. So domain consists of that finite sequence. Obviously, we have now finite sequence C1, C2, Cn, and all C1, C2, Cn are elements of now from the pi base. Okay. So that's you can always do. Like instead of pi base, let's say think about the basis. Like you can play the whole game using the basis open sets. You don't have to work with the open sets or space because you have the refinement strategy. Okay, so you may say that okay, why we should play? Because if K is a winning strategy for the alpha, any refinement of T will also be a winning strategy for the alpha. So if T is a winning strategy for the player alpha, then any refinement sigma of T is a winning strategy. Because if you consider a sequence like Bns, where Bns are from the domain, so let's say consider a sequence Bn, n belongs to 1, let's say this is a T plate, where, okay, let me put K, where B1, B2, Bn belongs to domain of sigma n for each n. Correct. So now because it's in the domain of sigma n, it's also in the, so this implies that B1, B2, Bn also belongs to the domain of Tn for each n. That means what? That is Bn is a key play. Sorry, it's a sigma play. I need to say sigma play for this. So this implies that Bk K belongs to this is key play. Or actually, you don't have to write because every sigma we already by construction every sigma play is key play, and a player alpha has a winning strategy. With T winning strategy means each key play is owned by the player alpha. So obviously, it should be owned when all sigma play are key play. So it should own all the sigma play. So you don't have to go through this already. By definition, it is coming. Okay. So that means if you have a strategy, winning strategy, you can always refine it, that strategy. That's also going to be a winning strategy. That's the thing. Okay. Now we have this characterization, so theorem. We will not prove it because we don't have time. So, but its proof is little complicated. One part is easy, but another part is little complicated. It says that if we have a bare space, let X be a bare space. Okay. Let X be a topological space. Then X is a bare space if and only the player beta has no winning strategy in the Shoke game. Okay, so if the space is a bare space, the player beta has no winning strategy. It does not mean that player alpha has a winning strategy. It's just saying that the player beta has no winning strategy. Okay. So alpha always has a chance in this case. Okay. So this is our characterization of bare space using the game theoretical notation. So, it's a very interesting result, and it has many consequences. Right? It has vast application in metric space analysis. Like when we discuss continuity, multivariate function, it has many applications.
Why the requirement of strategy is required?
Because suppose a topological space not given in terms of open set, but in terms of basis area. So that's why we were thinking about. But sometimes you need a refinement for proving some strategy. Or suppose you are working with a strategy. Okay. So suppose you design a new strategy because you are always changing something. So maybe that time you need a refinement.
You might have many strategies for winning, but usually when we consider the best strategy.
Yeah, but here you can have many strategies. Like baseness is not defined that way, so you just refine it sometime. Like, it's helpful in improving some theorems or like that, or you just want to get something you refine. Suppose you know vaguely this is my strategy, and okay, we refine it and make a new strategy.
What exactly?
Refinement means suppose we have a strategy, we are just deleting some elements like that. From a domain, we are deleting some element and taking. Yeah, like you can have so many possibilities, so many. You're just deleting some and taking only few considerations.
Example that you where alpha has a winning possibility. So if I have a sequence AB, 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 and then A, the refinement could be AB, A, like that.
Not like that, but because in a finite space it's really difficult because let's say I consider what we consider A, B, C, D. Okay. So we have tau as x phi A, B, A, B. Now if we consider the domain of T1, we have what all the possibilities is there. A, B, A, B, and X as well. These are all possible in the domain. So now, what is the domain of T2? So domain of T2 is basically whatever you consider as a B1, now your B1 is fixed. Then it depends on that you have A2. So let's say you fix your B1. So then you have A, and then this can be A, and then there is no other possibility in this case. Because only one substrate will be there, which will be inside of that. So then you continue this way, like that. Okay. So this is one thing. Okay. Now let's say I want to get domain of sigma 1, like let's say A, B, again you have A, B, and then X. And let's say domain of sigma 2. Okay. So now you choose B1 as AB. So if you choose B1 as AB, there might be a possibility that T1 and let's say T1 of AB is also like, what should I say? It's also AB, let's say. Or maybe only A. So now we have this. Okay. AB and A. In this case, actually, it's not coming like that. Yeah, then another possibility is that ABA, it can be. Okay, first element we should have same thing, otherwise it has no meaning. All you need to consider it's a complex process because whatever B1 you choose depends on that you have your possibilities. So here as well you have to choose for different B1 you have that, but thing is that I can't give you properly the examples. Let's go one by one. I think I made a mistake. Again, let's accept A, B, C, D, and your tau is I X A B A B. Then, what is domain of T1? Definition is it's all possible non-empty open set. So X A B A B, and domain of T2 is like B1 B2. So just let me write it B1 comma B2 such that B2 is an open set. B2 is an open set and B2 containing B1, where B1 belongs to domain of B1. Correct. Now you have to consider so many possibilities. Like let's say B1 is X, then your X depends on that you need P1 B1. Okay, and then from P1 B1 you need the B2. So it's writing down all these possibilities. Difficult choices. Okay.
We have X, A, A. So the domain of T2 is X, comma, all the possibilities.
X comma all the possibilities. If A1 is a B1, then you have all the possibilities. And if it is B, then you have all the possibilities. Like that. Like that it is coming. By the way, why refinement then? Not sure about the domain is same. So you can think about it like you have a basis element and from there you are generating the topology. So your new refinement is just a basis. Just you are working with the basic open sets. You can think about T is working with all possible open sets, but the sigma is like you are working with only open intervals. You can think that way. Instead of working with all the things, it will be like that, I guess. Okay, at least let's say what is will be the domain of this. Let's say B1 is X. Then your T1 of X can be A, T1 of X can be B, and T1 of X can be AB, and also T1 of X can be X. So for this you have B2 has only possibility for B2 is A. For this you have only possibility for B2 is B. For this you have only possibility is A, B, and AB. Okay. For this we have possibilities, all the possibilities X, A, B, AB. So we have to write down all this thing and we get a that is the domain of this. Okay, I have to think about because refinement is something new people have defined. So maybe there is some sketch. Not sure. Because whatever we are taking is the same domain. Thing is that I think that's a redundant statement that domain of En is subset of domain of sigma is subset of domain of En. Because in both cases we are getting the domain, same domain. Only thing you can change is the value at any particular sequence En of that, whether that is subset of En of B1, B2, Bn or not. That you can have. That functional values, like you see, the T1 of, let's say we consider T1 of X is, okay, why I put X? Yeah, X can be like all this. So we have sigma 1 of X, whether it is a subset of T1 of X only. That might be a case, like for particular play, particular sigma play. Okay. So a particular sigma play you choose like, let's say A, B. Okay. A, and then B. Then you may ask why sigma of X is a subset of T of X or not. So that might be a possibility. Like whether that particular T play, yeah, sigma play is an T play or not. Domain will be the same. I think refinement and this domain will be the same. That statement is a redundant statement. The domain of sigma A is a subset of domain of Tn. The next part is important, like sigma n of b1, b2, bn. That's why you have a new function, whether it is a subset of Tn of b1, b2, bn or not. That might be defined case for a particular chain of. When you are considering a T play or sigma play, is a chain of sequences. Now, in that sequences, consider any finite number of terms. In that terms, where sigma is mapping and T is mapping, whether the element you are getting for sigma is a subset of mapping for Tn or not. That's the domain is not important. It's a domain will be the same both cases. But whether the mapping is same or not. Let's say you have some play like AB, then you have AA, Okay. So this is a chain of sequences. Let's say T1 of AB is obviously definitely should be A. T2 of A will be A again, like this. In this case, sigma is okay, but let's say sigma of AB, let's say could be. Then that sequence obviously not a refinement of this because this value is not inside of this value. But same play, same sequence, okay. It's also in the domain of Tn and domain of sigma n, okay. But this T play and sigma play are different. That's why this is not a refinement. That's the case. But let's say you all have AB. In AB, I mean, it's might possible that here it's mapped to AB, one plane. Then for that, what will happen? That's we also have to check. AB and O, it's like A and then it's B, so it's containing in other set. So that is the case. Like only thing you need to consider whether sigma n of b1, b2, bn is a subset of Tn of b1, b2, bn or not. If it is so, then okay. I think let's conclude this session because I think it's really for you. Okay.